Hi everyone, welcome back to the second part of our tutorial on efficient dispersion-corrected hybrid DFT and FHI-aims. The second part will focus on analyzing organic-inorganic perovskites. Hybrid perovskites have gained significant attention due to their remarkable photovoltaic efficiencies, even in single crystal forms. The term hybrid here refers to the combination of both organic and inorganic components within these materials. A well-known example of a hybrid perovskite is methyl ammonium lead iodide, or MAPI for short. Like their inorganic counterparts, hybrid perovskites adopt the ABX3 structure. In the case of MAPI, the structure consists of a methyl ammonium cation, Ma, a lead cation, and iodide anions. This here is the structure of MAPI. The purpose of this tutorial is to understand how to simulate a complex material using density functional theory and analyze its electronic structure. The workflow consists of 3 steps. First, we'll find and analyze the experimental structure of the compound. Next, we'll create the input files for FHI-aims and optimize the structure. And the last part is analyzing the electronic structure of the material with hybrid density functionals. We'll start by finding the target input structures. The orthorhombic crystal structure at low temperatures, including the atomic positions, was, for example, identified by Whitfield and co-workers in 2016. The crystal structure can be obtained from the Hybrid 3 database, which you can see here. Please expand the atomic coordinates and copy them in the geometry.in file. The original experimental structure contains deuterium atoms instead of hydrogen atoms. Change the species in the geometry file for all deuterium atoms to hydrogen atoms simply by replacing the character D at the end of the lines with H. And that's it. We have prepared the input geometry.in file for our first simulation steps. When starting from experimental data, the initial input geometry is often far from the actual equilibrium configuration. Therefore, it is advisable to first employ computationally inexpensive methods to refine the structure. For instance, one could use density functional theory with low precision numerical settings to quickly approach a better configuration. This hierarchical approach with FHI-aims might involve an initial relaxation using light species defaults, followed by a more accurate relaxation with intermediate species defaults. Alternatively, to further reduce computational cost, force fields can be employed for pre-relaxations. Force fields are often several orders of magnitudes faster than DFT-based relaxations, making them an efficient option for initial structure optimization. Recently, foundation models, which are machine-learned force fields trained on extensive datasets that span a wide range of elements across the periodic table, have become increasingly popular and accessible. A comprehensive overview of available force field models can be found through the MAPI Discovery project. The relaxation with the MACE MP0 force field is also integrated into CLIMS. Please here create a new folder which we call 0 pre-relax MACE and copy the geometry.in file from the previous section into it. In this directory, then type the following command in your terminal. Here we use the CLIMS pre-relax function to run the simulation with fixed space group symmetry with the MACE MP0 force field until the residual forces are smaller than 0.005 electron volt per angstrom. As you can see here when running the command, the output shows one line for each relaxation step, with the total energy and the residual force component given in the last 2 lines. For each step of the relaxation, a geometry.in.nextStep file is created with the corresponding structure of the specific step. The last step here contains the final pre-relax structure. In this case, the realization took a total of 68 steps. We then continue to refine the structure from the force field with DFT-based methods in FHI-aims. In this section, we will relax the atomic positions and the lattice vectors using the PBE+TS method. Please here create a new folder, 1 PBE light dense relax, and copy in the last structure from the pre-relaxation, i.e. geometry.in.nextstep.68. Next, we will create the control.in file that specifies all the needed runtime variables and numerical choices. It looks something like this. The flag XC here sets the exchange correlation functional to the PBE functional. Additionally, the flag van der Waals_TS activates the computation of the Tkachenko-Scheffler dispersion correction. The flag relativistic here sets the level of relativity to be atomic Zora scalar. The flags relax geometry and relax unit cell then activate the relaxation of the atomic positions and the lattice vectors respectively. We will use the light dense species defaults in the following, and these species defaults use the basis from the light species defaults, but a better integration grid. This is needed to get an accurate stress tensor and forces leading to energy and force consistency. As a next step, please submit the calculation to your compute resources. The calculation will require about 128 CPU cores and finish the relaxation in about 10 minutes. After the relaxation is finished, we can investigate the final structure. Here, CLIMS can again be a helpful tool. We use here the CLIMS unit cell info comment to get some information about the geometry file. The symmetry threshold is set to 10 to the minus 2 angstrom, which is roughly our chosen target accuracy from the relaxation from before. We find that the system remains in the space group 62 as predicted by the experiment. It is therefore a valid conclusion that the orthogonal phase of MAPI is indeed stable. As a next step, we will perform the density of states calculation and band structure calculations with Mulliken charge analysis. To accurately compute the band structure of the system, HSE06 has been proven to be a good choice in terms of reasonably balancing costs as well as accuracy. This system here contains heavy atoms, so it is important to also use an advanced relativistic scheme. Here, we will perform a hybrid functional calculation with HSE, with perturbative spin-orbit coupling for the eigenvalues. Let's take a look on how to set up such a calculation. The control.in file needs the following lines. The perturbative spin-orbit coupling has been activated with the flag include spin-orbit. The exchange correlation functional is set to HSE06 with the screening parameter of omega equals 0.11 1 over Bohr. We also request a computation of the total density of states with the flag output DOS, followed by the lower and upper limit of for the energy window, the number of points, as well as the Gaussian smearing. The same syntax holds for the species projected DOS, here specified by output species prosh DOS. Usually, the computation of the DOS requires a denser k-grid than the normal SCF cycle. We can use the keyword DOS k-grid factors to increase the k-grid in the post-processing step, here by factors of 3 in each of the 3 directions. That is, in the end, the DOS will be computed on a 15 by 9 by 15 k-grid. This will produce a converged DOS, however at the cost of needing more computational time. For a quick estimate of the DOS, it is also possible just to use DOS k-grid factors 1, 1, 1 instead. The subsequent block contains the band path along the high symmetry points in the Brion zone, which is chosen based on the convention by Setyavan and Kotarolo. We'll request a Mulliken projected band structure calculation, that is for each computed k-point along the path. A projection on each atom and orbital is performed. The syntax for the band output is as follows. The first 3 numbers represent the start point and the next 3 numbers the end point for the band segment, all in fractional coordinates of the reciprocal lattice vectors. The next number is the number of points per band segment. The last 2 letters are optional and represent the labels of the start and end point. We recommend to place these labels at the end of the line as they will later be used for plotting the band structure. Now it is again time to submit the calculation to your compute resources. After calculation is finished, a number of output files should have been written. The total density state is outputted once reference to the chemical potential, which are the .dat files, and also the original Kohn-Sham eigenvalues, which are the _raw.dat files. The extension .noSoc indicates the density of states files without spin-orbit coupling. Next, we here have also the L projected density of states for each species. The file extension syntax is the same as before. Then we also should have the band structure segments, again with the same file naming structure. And in the end, we also have the molecule projections for each K point in the segment. Here, only the projections with spin-orbit coupling included are written. To plot the molecule projected band structure and density of states, we will again use CLIMS. Here, the CLIMS-aims plot utility. This comment here will plot the molecule projected band structure and density of states projected on 3 groups: the lead species, the iodide species, as well as the Ma molecule, in purple, green, and gold respectively. Please feel free to play around with the styling. The resulting band structure is shown here. We can see that the valence band in the region from -4 eV to 0 eV can be assigned to the iodide atoms, while the conduction bands from about 1.4 to 5 eV are dominated by the lead atom. There is a direct band gap of around 1.4 eV at the gamma point. The HOMO and LUMO states from the Ma molecule, here in the yellow band, are around -6 to 6 eV respectively. To understand the effect of the spin-orbit coupling, we can also plot the band structures with and without SOC in the same plot. Here again using the CLIMS-aims plot infrastructure. The band structure with SOC is here plotted in black, while the one without SOC is plotted in red. We see that the band gap closes significantly by about 0.7 eV when SOC effects are included. Congratulations, you are now also done with part 2 of this tutorial. As we've seen in both part 1 and part 2, we learned how to run dispersion-corrected DFT calculations with FHI-aims, in particular with hybrid functionals for both molecular crystals as well as hybrid organic-inorganic perovskites. We hope this tutorial has been useful to you and you can use some of this in your future work. Happy simulating!